Earth science time. We're still talking about rocks. Today we're going to talk about metamorphic and igneous rocks today. I have a couple more things I want to talk about that relate really more to sedimentary rocks, but they relate to all kinds of rocks, so I'm going to have to remember to do those first. Some of these cowboys have made a flow chart of how to identify sedimentary rocks. So probably on your flow chart, I'm just going to diagram how I would probably do it, but we got some rock here, right? What's the first thing we do as far as identifying it?
Is it has any greens on it or something?
Okay, so we want to find out whether it is which of these three things. What three things?
Sedimentary. Sedimentary.
It's all sedimentary. Okay, yeah.
Specifically talking about
We're specifically talking about sedimentary from the flow chart. So it's we have somehow. Okay, when I say somehow, how would we tell that it's a sedimentary rock?
If it's got sediments.
Yeah, if it's made of sediments of one kind or another. So if it's a sedimentary rock, we've already determined that. How are we going to then? What are we going to do next? We're going to break it down into whether it is
Chemical,
or chemical. I'm going to put biochemical or clastic. Once again, your text uses the word organic for biochemical, but I most often see it as biochemical, and as far as I can tell, they mean the same thing. Once we have determined whether it's chemical, biochemical, or clastic, then for instance, if it's chemical, we then identify it. If you give me just some examples of chemical sedimentary rocks that we could say it is. And of course there would be ways to identify which of those. What are some examples here for chemical? Limestone. I'm going to put etc. on the last one because there are more. But what are some others? I can think of at least two others. Rock salt. Gypsum, which we saw in the museum the other day, is one. There's also chert. By the way, gypsum is calcium sulfate, where, if you remember, limestone was calcium carbonate, CaCO3. Gypsum is calcium sulfate. Gypsum is also what makes up drywall, and I think plaster. Even this plaster, look at this. This is a nice plaster. That's probably calcium sulfate too. Rock salt, what's its chemical composition? It's some kind of metallic halide, but it's usually sodium chloride. Metallic sodium halide. Remember, chlorine is a halogen. And then chert, what did we say chert was? Some kind of silicate. SiO4, 2 It's going to have a silicate group. And then there are others too. In biochemical, what might it be? I'm going to put etc. on one of them. What might it be in biochemical?
Well, it's formed by life, and it could be fossiliferous limestone.
Yeah, it could be fossiliferous, really anything. Fossiliferous.
Anything.
I'm also going to put, fossiliferous means it has fossils, but I'm also going to put up here coquina, which coquina is, if it is entirely made of fossils. Like if it's a whole little lump, a little mountain of fossils, that's called coquina. Or some people say coquina, it depends on. It's not cocaina, that's cocaine. It's coquina if you're using the Spanish pronunciation, or coquina if you're using the British English pronunciation. And then there's also things like coal, etc. And then within clastics, what's the next thing we break it down into? And that's kind of funny. Break it down, plastic, geology jokes. I wish someone had laughed at that. But what do we break it down into for classic sedimentary rocks then?
Is that the one where they're by lithification?
Yeah, they form through lithification.
That's when we categorize them by grain size.
Yeah, grain size. And what are the main grain sizes we usually use? Pebble. Sand. Silt. Clay.
So like, Mr. Cotton.
And then pebble could be either.
Look at what I did for my voting. So I only did what was for clastic, I guess.
Okay, yeah. So you did plastic sedimentary rock only, but that's exactly what I was going to put here. So if it's pebble,
we need to know if they're rounded or angular.
Yeah, rounded. So it could be conglomerate if they're rounded,
or breccia,
or breccia if it's angular. This might help you. It helped me. To me, conglomerate just kind of sounds like a round word, like a bunch of little circles stuck together. That's what the word conglomerate sounds like. But breccia is the Italian word for broken. So that might help you. It looks like chunks of broken up, like jagged, angled shapes of rock. Sand we call sandstone, if the grains are sand-sized. Silt we call siltstone. And clay we call shale. Okay?
Okay.
Here's something that I was going to get that's true of all rocks. Let's talk about something that's true of all rocks. Not just sedimentary rocks, but it is true of sedimentary rocks too. But let's talk about this idea of porosity. Porosity. What is this word probably related to? Absorbent and yellow and porous. What does that mean?
That he has holes?
Yep. Porosity is relating to pores. You have a certain porosity of your face, don't you? Some people have larger pores than others. TikTok tells me that I'm supposed to think it's better if I have smaller pores, so that really gives me low self-esteem. But porosity means relating to pores. It's the amount of pores something has in it. Amount of pore space. Why might this be especially important in sedimentary rocks? Yeah, sorry. Why might this be especially important in sedimentary rocks?
Because sedimentary rocks have like sediments. Like they're made up of different pieces so they can have like space in between them.
Yep, generally they have more pore spaces. On average, sedimentary rocks have larger pore spaces, especially when we talk about things like sandstone and siltstone. So how we measure pore space is we compare. There's kind of some kind of fun math that we do about it. But if we imagine sandstone looking like this is magnified. Remember, we usually use dots to represent sandstone, but I'm magnifying it here. And we could even do this in the lab. If we have a certain amount of sand in a beaker or graduated cylinder, we could also pour in water, and that would just kind of seep in the cracks. You know, sometimes your mom, or at least my mom, would say that about dessert. The dessert just seeps in the cracks. So we could pour water in here, and the water sits in these pore spaces. Does that make this rock not solid? Is the rock now water? Is the rock acting like liquid? No, it's still a rock. It just has some liquid in the pore spaces. And this is actually how an aquifer works, usually. There are other kinds of aquifers, but this is how an aquifer works. When we have an aquifer from which we're drawing water, like when we do the Know Your Well program, that's usually a well has been drilled into the rock itself. And if you were to go down there, which you can't, but if you were to go down there, it would just be rock. You wouldn't fit because you don't go in the pore spaces. But the water does. And so when the well is drawing, it's just drawing water up through those pore spaces. And that's the pore spaces, the amount of pore spaces compared to the amount of rock is called porosity. And generally, what kind of rocks have the higher porosity? Sedimentary, generally. Why? Why might metamorphic and igneous rocks, we haven't talked about either of those yet, but why might they have less pore space?
Well, like what I think for like igneous is that their crystals can be a lot closer, and so they don't have the space to like.
Yeah, there can be pore spaces in igneous rock. In fact, there's a kind of igneous rock called pumice or scoria that it's lots of pore spaces, lots of holes. It looks like a sponge. You've seen pumice, and that's an igneous rock. But that's formed from bubbles in the magma. But usually the magma, a liquid, is just sitting there, and then as it cools, there's no room for crystals to have anything other than crystals between them. Same thing, metamorphic. Remember, metamorphic rocks form from enormous heat and pressure. So if there's enormous heat and pressure, it's probably going to squeeze out the air or water, whatever's in the pore spaces first. Think about a sponge. Absorbent and yellow and porous is heat. You got a sponge with pore space. If you put a little bit of pressure on, the pore spaces necessarily decrease. That's the first thing that happens when you compress it. Another thing relating to sedimentary rock that we want to talk about is this idea, I'm just going to put it up here kind of as an aside, of bedding. What's bedding mean? In your daily life, what's bedding mean?
Like what's on my bed.
What's on your bed? Let's draw a picture of the bed. Minecraft bed, first we put on the fitted sheet. This is not going to become a how to make the bed podcast. But first we put on the fitted sheet. And then this is how I do it at least, then I put on the flat sheet. And I put I don't curl this over yet, but eventually I will. Then I put the little pillowcase on the pillow, and I put the comforter on. And then I fold the little sheet over top of the comforter so that when you get in, you don't have to have any part of your nasty little puberty-stricken body touching the actual comforter, because you don't wash your comforter as often. My philosophy of make the bed is I don't want any part of my body to touch the comforter because I don't wash it as often, so it's all about the sheets. Anyway, that's bedding. And one thing about this kind of bedding even is that it is, I would say a verb we could use for this is that it is layered. And that's true of rocks too. When we talk about bedding in rocks, we're talking about how, for instance, if we have a river, this is just an example, it doesn't always happen and only in rivers, but as an example, we have this river, which apparently is lava because I'm using red. I'm going to switch colors so that no one thinks this is lava. We have this river, and the river is carrying sediment, as we know. Remember, we talked a little bit about weathering and erosion, but the river is carrying sediment. And as the river slows down, which it does for a number of reasons, but you saw this on our field trip when we went to Sunday Gulch, remember? But as the river slows down, the sediment falls out. Say this is the ground. The sediment falls out of the river. Say this is slow. The sediment falls out of the river. And the order in which this sediment falls out, or whatever the grain size here, this property of the rock here is called its bedding. The way the rocks line up due to an erosional medium is called bedding. The layering of sedimentary rock due to erosional medium. And the last thing I want to talk about before we really get into metamorphic and igneous rocks is related to this. It is just the very basic idea of weathering and erosion, which we touched on yesterday, but I want to make it abundantly clear. Weathering, let's define that. Someone should already know this. And erosion. We're going to define that too. Are they the same? We group them together a lot. Maybe even when you were in elementary school, someone told you it's just weathering and erosion. Like this, what happens to the rock is called weathering and erosion. But what is there a difference, first of all? Yes or no? Is there a difference?
Yes.
Yes. What is the difference? Well, what is weathering?
Weathering is like when the weather affects them?
Not necessarily. They come from the same root word. It's the other way around. Erosion, let's put that right now. Okay. Erosion is the transport of sediment.
And weathering is breakdown.
Yeah, and the weathering is the breakdown of what?
Of rock.
Rock. Usually rock. It can be a lot of other things too, but we're going to put breakdown of rock to form sediment. So this is the process by which sediments form. And erosion is the process by which they're transported. And then we also have its little, like, ugly redheaded stepchild, deposition. And I don't think redheaded people are ugly, first of all. Sorry, Tesla and Vogel. I do not think that. But I mean that not also because this is not an important process, but it is often forgotten. Kind of like poor Kesslin, God bless her. We all should be nicer to Kesslin. It is often forgotten. But I want to mention it because deposition is for one thing, it's the end of erosion. Wherever the rock material, the sediment, ends up, it has been deposited. But it's actually this process that makes the rock able, that's how the sediment all gets in that little pile that eventually becomes lithified and forms a sedimentary rock. Good thing my lavalier mic ran out of battery, so now everything that happens in this room can be heard by everyone all the time. Weathering breaks down rocks to form new sediments. Erosion moves those sediments, and deposition is when the sediments stop moving, where they end up. If they are deposited, does that mean they're there forever? No, erosion can resume, or when that rock is lithified, or when that sediment is lithified to form a sedimentary rock, that can then be broken down and eroded. It's a continual process from the rock cycle. I would say if you leave earth science knowing one thing, please know the difference between weathering and erosion. That seems almost pedantic. No, it's not like It's not like there's going to be some guy on the street robbing you and saying, "Tell me the difference between weathering and erosion, or I'll shoot you." He'll probably say, "Give me your money, or I'll shoot you." But to me, this is important. You understand the difference between these processes. Let's now, because we just talked about lithification, let's talk about lithification's
Homeboy?
Yeah, homeboy, big scary motorcycle homeboy metamorphosis. What's metamorphosis mean as a word? It's from the Greek. Meta meaning, what do you think? What's meta? What, like in a metaphor? What's a metaphor mean? Or
Like an exaggeration or
a metaphor. A metaphor is something that you use, and this is where the word comes from. It's to carry across your point. Metaphor, that literally means to carry across. Meta means across. Morphos is the Greek word for shape. So this kind of, in almost a metaphorical sense, means to change shape. Not literally meaning the actual shape of the rock, although that usually does change too, but meaning its nature changes, the form of it changes. The form of a rock changes. Always a sedimentary rock? Question mark? Always a sedimentary rock? No. Always a sedimentary or an igneous rock? No. Even a metamorphic rock can undergo further metamorphosis, as we'll see in a second. In fact, that's a very, very, very important part of metamorphic rocks. The form of a rock changes through usually what processes? In fact, I think always through what processes?
heating and cooling?
Yeah, heat and pressure. Not melting. Does that mean that a rock can't melt? No. I mean that if it does melt and then crystallizes, that's not a metamorphic rock anymore. That's an igneous rock. Yeah. Not melting. So we want to make that very abundantly clear. But there are grades of metamorphism. I'm going to have this arrow going down here, meaning more heat and pressure. Kind of above metamorphism. It's not metamorphism at all. So above this little list, we have lithification. Lithification is due to pressure, but it's not considered a kind of metamorphism. Lithification, remember, is pressure put on sediments with cementation that causes those sediments to then stick together and become a rock. So lithification is up here. But then we have these different low grade of metamorphism to high grade of metamorphism. So let's start with, we're going to do this two different ways. Let's start with a pile of sand. We've got a pile of sand up here. So the beginning thing, just the sediment, is sand. As the sand is lithified, compacted and cemented, it becomes what?
Then it becomes silt? Or
No, if it's sand-sized particles, yeah, you might have to look back at your chart.
silt?
No.
Pebble? What?
No, the sand. Sand is the grain size. We got a little pile of sand. And it's
Sand
gonna,
is a grain size.
yeah, sand is the grain size. It's going to become compacted and cemented to form what sedimentary? What sedimentary?
That's what it said right here. That is our example.
No, it shouldn't be. Because what if you have sand and they come together? That makes sandstone.
That's what I said, Mr. Kyle.
Oh,
I literally said sandstone.
I thought you said siltstone like 3 times.
No.
So yeah, sandstone. You're right, Kyle. I really thought you said siltstone. Anyway, so through lithification, the sand can become sandstone, and then with heat and pressure, in low-grade metamorphism, that can become quartzite, and then through more heat and pressure, that can become phyllite, and that can become schist, and in the highest grade of metamorphism, it can become gneiss. And the gneiss has kind of like this zebra stripe pattern that we associate with it, because what's happened is the very chemical constituents that make up whatever rock it was have separated out. Kind of like when you have that density experiment where we layer corn syrup and then water and then soap and then oil and then alcohol on top. You've seen that, right? You know what I'm talking about, where you put those things all together and it makes little layers. In the same way, they separate out by density in the gneiss, which is striped. We can go at this a different route. If we started with some kind of claddy minerals meaning flat. This means flat. If they are lithified, if these platy minerals, some flat minerals are lithified, what do they become? They're very small, clay-sized. In fact, clay has to be flat. What do they become when they're lithified? Some clay-sized material. God bless you. God bless you. What sedimentary rock does clay become when it's lithified?
Clay.
Clay. Shale. Clunk. And then when that becomes low-grade metamorphosed, we say it is now slate. Clink. And then if slate undergoes further metamorphosis, it becomes phyllite, which then becomes schist, which then becomes gneiss. What if we, instead of starting with a sedimentary rock at all, we come at this from a different angle, and we start with an igneous rock? Let's say granite. Granite's over here. We're going to talk about granite in a little while. But granite is an igneous rock. And if it undergoes metamorphism, it becomes phyllite, and then it becomes schist, and then it becomes gneiss. So all these things can undergo metamorphosis to become these metamorphic rocks. And these specifically are the foliated metamorphic rocks. Even coal can undergo metamorphosis, and that we call then anthracite, which is another kind of coal. But what if the chemical makeup of the sedimentary or igneous rock is not diverse enough to lead to these foliated, these striped? Remember, the word foliated means like a pile of leaves. That's what foliated means, like it's related to the word foliage. We've got just these little layers in it. That's what foliated means when we're talking about metamorphic rocks. But what if the chemical constituents of the rock do not lead to foliation? What if they aren't separated enough, or they can't be separated enough? Well, then we have a situation like if we had limestone. Let me draw a line. If we had limestone. Well, if limestone undergoes those same grades of metamorphism, limestone's already a lithified sedimentary rock. Let me carry this over here. It becomes, does anyone know? What does limestone become under metamorphism?
Does it become...
You might remember from your lab, is the only thing I can think of, or maybe from last year, if you were here last year. It's non-foliated. It's marble. Marble is also just like limestone, calcium carbonate. It's just metamorphosed. Metamorphism causes rocks to be a lot denser, usually, a lot less pore space, usually more chemically inactive. For instance, the mineral calcite that makes up limestone will fizz if we put hydrochloric acid on. You've seen that. You remember that, right? Mm-hmm. And then when that rock is dissolved in water and recrystallized and becomes limestone, that will still fizz when we put acid on it. In fact, even more probably, because it'll be less condensed. But if we compact it to form marble, that reacts much less readily because the atomic structure of the marble is closer together. There's less surface area available for reaction with acid. But what causes all this? You might ask yourself. Are you asking yourself that? Why would anything ever undergo metamorphosis? Just a strong guy with a microwave squishes things and then heats them up? Yep. You got it. Okay. End of video. No. What might cause metamorphosis? We know it's caused by heat and pressure, but where at? Or what's going on? Or how does that happen on Earth? If it were a volcano, why would it not be a volcano? It does happen in a volcano. I'm going to get to that in a second. But why would it not? When you say in a volcano, you mean the lava. Why would it not be the lava?
Because it's not magma.
Yeah, because if it melts and then cools out, it's an igneous rock instead. But what we do get from that, I'm going to erase this. And I'm already erasing it. So, what we do get in a volcano, or what we do see in a volcano, is this idea of baked rock. We'll get to volcanoes more specifically in a second with igneous rocks, but there are three normal and one super cool way that metamorphism can occur. Types of metamorphism. The most usual, I would say, or the largest by percentage of rocks formed this way is regional, which is where plate tectonics, the action of plates, are causing pressure to be on rock. And in places where that pressure and heat does not cause the melting of the rock, the constant pressure and heat without melting causes metamorphism. Another way is what we call baked rock, or contact, and that's the more professional term, but contact metamorphism. And this is caused by, there is magma, but it's the rock that doesn't actually melt. It's the rock that's around the magma that is very hot and probably under quite a lot of pressure, but not actually hot enough to melt. That's contact metamorphism. So rock touching magma without melting. And then the last, I would say, usual way is called hydrothermal metamorphism. And that's similar to this, except when it's touching superheated water. You'll remember from chemistry that when it's under enormous pressure, things like water that are liquids can get much, much hotter without turning to steam than when they're not under pressure. So under Earth's surface, water can get thousands of degrees because it's under pressure without turning into steam. And that superheated water, when it touches rock, can cause changes of metamorphism. And then the coolest way, I'm just going to put a star for this one, the coolest way is impact metamorphism, which is where asteroid or some other heavenly body smashes into Earth, and most of the rock is melted or even vaporized, but the rock that's around that undergoes metamorphism because of the enormous heat and pressure of the impact. We have regional metamorphism, contact metamorphism, hydrothermal metamorphism, and then super sexy impact metamorphism. Do you understand how each of these would lead to the rock being heated but not necessarily melted? And you see how each of them could lead to pressure, because that's an important part of it too. Okay, and then the last thing, I'm going to probably do this over in this little corner so that we're going to still be copying down the types of metamorphism, is we have igneous rocks. How do igneous rocks form? Melting and crystallization. Good. And that can happen in one of two places, really. From magma or from lava. And what's the difference between those things?
Magma is inside the earth and lava is outside.
Yep. We call the magma ones, we call these plutonic or intrusive. And we call the lava one volcanic or extrusive. And you should remember this from last year if you were in Earth Science already, you might even remember it from our trip to the museum. What's the main difference visually or physically between these two things? Like, how could we tell? We can't go, bless you, we can't go back in time and look at how a rock formed. So what do we see about the actual rock that tells us whether, yeah, exactly, which one's which?
Big crystal is intrusive.
Yep, big crystal is intrusive.
Crystal is extrusive.
Big crystal and small crystal is extrusive. Think about it this way: the inside of Earth is warmer, and as the magma cools, it forms crystals. And since the inside of Earth is warmer, it takes a longer time for it to cool. If it's on Earth's surface, which is cooler, it takes less time, and so the crystals don't have enough time. And that's the next thing is that the atoms rearrange themselves to form crystals, but that takes time. So the less time they have, the smaller the crystals can grow. The more time we have, If I had a chair right now, I would climb up on it and get those. We have crystals from last year growing still in this closet. You remember? In those little tubes?
Yeah.
And we had ones that were in open containers, and those grew relatively fast. And then we have ones that were in very narrow containers that are still growing to this time. They're more than a year later, they're still growing. They're still growing.
Really?
They're going to form extra large crystals because they've been growing for so long. Of course, those ones are forming through evaporation. That's forming a chemical sedimentary rock, whereas these are forming from cooling. I'll just leave it there for a second. That's one way that we organize metamorphic rocks. What's the other? We organize them by their grain size, by their crystal size, but also by there's one other binary state that's not quite binary, but there's one other categorization we do for igneous rocks. Do you remember what it is?
No.
Okay, I'll tell you what it is. It's their composition. And we have two compositions that we usually talk about. We have felsic and mafic. There is also an intermediate. And these are their composition. Felsic, and the way we tell it from the actual rock is that by looking at it, is the felsic is light and the mafic is dark. So using these two pieces of information, well actually let me remind you of this. Felsic stands for feldspar and other silicates. And mafic stands for manganese and iron. These are not the only things that make them up. These are kind of like old-fashioned-y terms because they're not the entirety of what's making them up, and there are other kinds that have no feldspar or have no manganese and iron. But generally, we still use these terms. Felsic meaning it's made of feldspar and other silicates, which causes the rock to be light, and mafic meaning it's made of manganese and iron, causing the rock to be dark. And so now we have this little table of intrusive versus extrusive, and then mafic and felsic. Intrusive felsic, large crystals that's light colored, is granite. Mafic that's intrusive is called gabbro, so dark colored large crystals. Mafic that's extrusive is called basalt, so dark color small crystals. And felsic that's extrusive is called rhyolite. There are others. There are intermediate ones, diorite and andesite, respectively. Diorite is small grained and andesite is large grained. And then there's also glass. Ones that cool instantly, like obsidian, is glass. Ones that have bubbles in them are pumice or scoria, depending on if they're felsic or mafic. Pumice is felsic, scoria is mafic. And then there's also this idea, and this is the very last thing that we're going to talk about, is porphyry, where it has large crystals in a small crystalline matrix. So kind of like a chocolate chip cookie. It's fine grained, except it's got these big old lumps of large grains in it. And we call that a porphyry. And that happens when one kind of mineral cools earlier, and so it has a longer time to make large crystals, and the rest of it kind of cools around it. There is stuff on your test about obsidian, pumice, those other kind of rocks I mentioned, and porphyries, and there's also stuff on your test about Bowen's reaction series, which I will kind of walk you through as we're doing the test. There's only one question about that, and to me that's kind of upper level knowledge, and that's actually what I wanted you two girls, Earth Science 2, to do a little report on, was Bowen's reaction series, so we'll talk about that a little bit more tomorrow. But do you have any other questions that are for the good of everyone?
No, sir.
About metamorphic or igneous rocks?